Okay, well, yeah, we'll get started. I'll talk a little bit about the final exam, and then I'll talk a little bit about the Monopoly homework assignment, and maybe a little bit more about randomization and Bootstrap. And then if we have time left over, I'll talk about another topic that's not, you're not going to be tested on, but I think is useful in your statistical education here. So, okay, so let's talk about the final exam. Okay. So the final. Okay, it's going to cover stuff from after the midterm. So covers topics from after midterm. Okay, so that includes root finding methods, and optimization methods. Okay, root finding methods, optimization. Also, randomization tests. And bootstrap tests. Okay. And some of these you will need a calculator and a ruler. Okay. So because for some of these I'll have you carry out certain steps manually, like to make sure you understand how the either the root finding algorithm works or the optimization algorithm works, and so you'll need to do that with a ruler, right? You'll say, okay, if I give you this arbitrary starting point, I'll say, carry out this, this root finding method, carry out 2 or 3 iterations of it, and you'll have to say, okay, well, if we're at this point, then at the next iteration we'll end up at this location, and at the next iteration we'll end up at this location, something like that. Okay, so for that you'll need a calculator and ruler, and that's for the root finding methods or optimization things. For randomization tests and bootstrap tests, you will probably have to freehand write code. Okay, so to kind of and so pretty much what you would type into R, but you would write it out by hand, and the syntax and all of that, it counts. Okay, so your code needs to be syntactically correct. Okay, now I'm not going to do this, but it should be correct so that if I were to type your code into the computer, it should run without problems. Okay, now I'm not going to go through and type every single person's handwriting into the computer, but I feel like I have a fairly good grasp of what happens in R, and so if there's some glaring mistakes, I think I'll recognize them. So so you'll have to go through the code. I mean, you'll have to, when you write, you'll want to make sure you're you're following things correctly and make sure that it works. Okay, and that will probably cover your randomization tests and bootstrap tests, and you want to make sure you do understand kind of the methods and whatnot there. Right. Are there any questions on this? Yes.
Is RVest going to be?
I am not planning to put RVest on the finding. Okay. Okay. Is that all right? Okay. Guess I'll save that. All right, let's take a look at your Monopoly assignment. I wanted to kind of explain this a little bit deeper, and I know a lot of you guys have started it. Maybe some of you are struggling to get started. I don't know, but I posted some kind of like sample code, some starter code. You're not required to use that, but if you aren't sure how to get started, it could be helpful. So let's see. All right. Okay, so for the Monopoly assignment, all you're going to be doing is you're going to just keep track of player movement. Okay, you start at, everybody starts at go, and then you just go around the board. The board has 40 spaces on it. You roll 2 dice, and you move that many spaces. And there are a few rules for how the movement goes. Okay, so let me just copy this. This is the image of the Monopoly board. Okay, so everybody starts here. There's 40 spaces, and one of the spaces is jail. There's like 2 modes of jail. Like you can land on the jail space and it's just visiting. Okay, you're not in jail. And then other times you are sent to jail and then you are locked in jail. Okay, so if you land on this space, you get immediately sent to jail. Okay, and so what we're going to say is that this space can never actually be landed upon. Okay, as soon as your dice takes you there, you get sent to jail. So when we tally up the board counts, okay, you're supposed to keep track of where every player has landed. This spot should have a count of 0. Okay, so if you have a tally, anything other than 0 here, you've done something wrong. Okay. Let's see. Okay. Anyway, rolling doubles. If you roll doubles, which means you got 2-2 or 4-4, you got 2 of the same number, then you get to go again. If you roll 3 doubles in a row, on the 3rd time you roll doubles, you immediately get sent to jail. You don't actually move those numbers as spaces. If you roll, the first roll is a 2-2, the second roll is a 6-6, and your 3rd roll is a 4-4. As soon as you roll that 4-4, you are sent to jail. Okay. There's also these chance and community chest spaces, and when you land on these spaces, you draw a card. A lot of times the cards tell you, get some money or charge another player or something like that. But a lot of the cards also move you to other spaces on the board. Okay, and so we're going to say if you land on one of those spaces, it doesn't count as having landed upon until your turn ends. So if the card keeps you, like if you draw chance and it says you won 2nd place in a beauty contest and it keeps you at chance, then you count a tally for landing on chance. But if it says, if you're on chance and it says advance to the nearest railroad, then you move forward to B&O Railroad, and then only B&O Railroad gets counted as landed upon, and we will say that chance is not landed upon in that turn. Okay, does that make sense? Okay, so yeah, there are some students aren't quite sure. There are 4 railroads. They each have the train on them. And there are 2 utilities. The utilities are waterworks and electric companies. So the chance cards, there are some that say move to the nearest utility. There are some that say move to the nearest railroad. So those are the spaces that correspond to utilities and railroads. Okay, and then as far as jail goes, if you are in jail, you have the option to pay bail or use a card to get out of jail. It's optional until it becomes your 3rd turn in jail. So you can stay up to 3 turns in jail. And so on your 3rd turn in jail, you have to leave jail. That's the rule. But you know, in the game, strategically, towards the beginning of the game, you probably want to get out of jail immediately so you can try to claim up other properties. And towards the end of the game, after all the properties have been claimed, it almost makes sense to remain in jail. For the purpose of our simulation, we're going to use a, quote, long stay strategy in jail, meaning you will remain in jail for 3 turns unless you get out by rolling doubles, okay? So when you're in jail, what happens is you roll the dice, and if you roll doubles, then jail will boot you. You get kicked out of jail, okay? So if you roll 6-6, then you will move 6 spaces and end up on St. James Place. But if you roll any other number, then your turn ends and you start in jail on the next turn, okay? So, and then after starting in jail for 2 turns, on the 3rd turn that you start in jail, then you get sent out of jail, okay? So what happens, so let's say, you know, you're over here, you start on B&O Railroad, you roll a 5, you end up on the go to jail space. Now you are sent to jail, your turn is over. Okay, the next turn is your 1st turn in jail. You roll a 7, you stay in jail. The next turn is your 2nd turn in jail. You roll an 8, but it's a 5-3, so you remain in jail. Okay, and then the 3rd turn, whatever you roll, you are now getting out of jail. So if you roll a 3, you still get out of jail. If you roll doubles like a 6, 3-3, you get out of jail. So that 3rd turn that you start in jail, you are getting out of jail no matter what, okay? Students have asked about the get out of jail free card. It doesn't matter, okay? Because that basically the get out of jail free card is just like a free $50, so you don't have to pay the money to get out of jail when you otherwise normally would have to. It has no effect on player movement, so you don't have to worry about the way it simulates in the game. Okay, does that kind of make sense as far as how the jail works? And yeah, so I've given you the data frames of the game boards, the chance decks, and the community chest deck. And then, and what I want you to do is I want you to kind of simulate player movement and keep track of where the players land, okay? And so I recommend using a reference class to help you keep track of what's happening. You're not required to do that, but if, you know, I gave some getting started code, which I think is helpful, okay? So here I'll go ahead and I'll run this, and so I've got 40 observations for the game board, and then the community chess deck and the chance deck. Okay, here I'm going to create a function called dice. Okay, and the dice, basically you just run it, and what it does is it's going to sample from 1 through 6 twice to simulate rolling two numbers, and then it's going, what it returns is a list telling you the numbers that you rolled, whether it's doubles, and how many spaces you move. Okay, so just as a quick check to see if the faces that you got are the same, and then if so, then doubles is true, otherwise doubles is set to be false, and then the movement will be the sum of the faces, and then if we have the verbose option turned on true, it will tell you exactly what happened. And what it returns is this list. So this is the dice function, and we just hit dice, and there you go. This is what it returns, and we can say dice for verbose equals true, and it will spit out rolled 2, 4. Okay, it will output that, and it outputs this step. Okay, and so dice just, it's a function to kind of see what we have, to just roll some dice here. Okay, now when you're testing, as you're programming this, a lot of times you want to test to see if certain parts of your code are working the way you want it to work, right? You want to see if I land on the chance deck, does it take me, does it follow the rules for chance? Okay, and when you're doing this, it can get really frustrating because you're like hoping for the random dice to roll a certain way, and if you do that, you'll probably get tired. And so I've programmed something called manual dice. Okay, and this allows you to set the dice that you want to go. Okay, and so you have what the dice here, the manual dice with a capital D, okay, is requires a few fields. Okay, the roles, the positions, and verbose. Okay, and this allows you to set the roles for the dice itself. Okay, so in this case, what I'm doing, using the manual dice, I'm saying these are the roles that I want to use, so that the first roll is going to be a 6-4, the next roll is going to be a 5-3. Okay, and so this way you can kind of set the index, or not the index, set a vector of what the dice will roll. Okay, so if you want to say, if you're starting at go and you want to say, okay, I want to see what will happen if I land on the first chance space, which is at space 7. Okay, then you can set your dice so that it's 3-4 or something like that. Or if you want to test out if the code that you've written for rolling doubles is working, then in your manual dice you can set a bunch of doubles. You can set things like 2-2 and 4-4 and 5-5, and you can see if you roll the 5-5 if it sends you to jail. Okay, and that way you don't have to just wait for the random simulator to produce these rolls that test out what you're trying to do. Okay, so let me just kind of show you how setting the dice works. So in this case, if you look at this code, this is, I'm calling a new instance of my reference class dice. I'm doing dice $new, right? New is a method that is inherent to all reference class objects to create a new instance of that reference class. And the dice thing requires 3 fields. And so, so I've got roles, position, we're going to start off at 0, and verbose equal to true. And we're going to call this to be set dice. Okay, and so now I have set dice, and we're going to create a function. We're going to replace our dice function, because currently our dice function is, random movement here. Here I'm going to rename the dice function, and it's going to be, the dice function is going to be a new function where it just calls the roll method within the set dice reference class object that I've created. So go ahead and run that. And so now I've replaced my dice function, and we can see that when I run the dice function, it's going to use the dice, the vector of dice that I have set here. Okay, so we can see, the very first time I call it, it tells me I got 6-4. The next time I call dice, it's going to say you rolled a 5-3, and then the next time it's going to say you rolled a 3-5. Okay, so we can see the reference class object is kind of working here, and part of your output that you will be assessed on for the Monopoly assignment is that you will use these manual set dice and produce the kind of the verbose output of what happens. And the verbose output of what happens should be, should show the exact movement, right? And so I have uploaded the kind of sample output of what should happen. So in that case, if you roll 6-4, I have the verbose output where it says, player starts at 1, go, player moves 10, player's now at 11, which is jail, okay? And we put a tally at jail. And then over here, we've got turn 2, you rolled a 5-3, player at 11, at jail, player moves 8, player's now at 19, Tennessee Avenue, okay? And it kind of shows what happens through all of this stuff, okay? Okay, and then it shows you kind of the tallies of all the different spaces that you landed. Although I think in this implementation, I had it count landing on chance. I'm gonna have to fix that. But yeah, so I'm gonna just update this in a moment because I realized I made a mistake as I'm talking to you. But anyway, this is how you can kind of check to see if your code is working, and this is also a way for me to evaluate and make sure that your code is working the way it should be by having everybody use the same set of dice rolls. I can make sure to see if your code is outputting properly. Okay, so that's the simulating the dice. Is that okay? Does that make sense? Both the kind of the random dice, which is what you're going to use when you actually run your 1,000 simulations or however many I asked you to do. Okay, you're going to use random for that thing, but then you're also going to run it again with the deterministic dice and have the output of those those set turns. Okay, as far as running the simulation, I've created kind of a very basic kind of a player reference class and a very basic tracking reference class. Okay, so you're going to have a player, and here you're going to want to expand this. Okay, but right now I just have within the player, I've got the only fields that I have in the player will be the current position on the board, and then a verbose option to kind of have a verbose output as far as the player reference class goes. There's probably other things that you'll want to have in the player reference class, you'll probably want to keep track of whether or not the player is currently in jail or not, or how many times the player has rolled doubles, or things of that nature. Okay, so those are probably some fields you'll want to add. And here I've got some very basic methods. I have two methods. One is move n spaces, move n, and the other is go to space n, which is useful for the drawing of cards. Okay, so move n, basically the only thing I do is say take the current position, which is in the field, is one of the fields, and then we're going to update that with position plus n. So move n is a function that takes in argument n, which is going to be kind of the movement value that appears on the dice. And we're going to say, if verbose, print this, player at such and such, player moves n spaces, then we update it, position plus n. And then, and here I say, if position is greater than 40, change the position to be position minus 40, right? So if you loop around the board, if you're starting at boardwalk and you roll a 3, then you're going to end up at, what, space 43 or whatever, okay? Then we need to update that to be, to do that. So we've got this thing that just says, if the position's ever over bigger than 40, subtract 40 from it, and then output on the screen, player is now at this position. Okay, and then go to space n basically just says, take the function where n now is the space location, and it starts off with players currently at this position. We update the position to be n, and it says players now at its current position. Okay, so this is just a very basic reference class object for the players. And then here we're going to create two new players. We just do using the player reference class, we call the method new, which is going to create a new instance of it. And here we've got player 1 and we've got player 2. And both of them we're going to say start at go, and verbose is true for both of these cases. So I've got player 1 and player 2. Okay, so now I have two players. These are my kind of reference class objects, player 1 and player 2. And then over here, I'm creating a very basic reference class for tracking, okay? And tracking is just, has one field, which is going to be the tally of the 40 spaces. And right now it only has one method, which is just increase the count for a certain space. And so it just says, if we end up at space 7, what we're going to do is we're going to increase the tally. We're going to take the current tally at space 7, add 1 to it, and update the tally at space 7. And that's it for the reference class for the tracking reference class. Okay, and then here I'm going to create a new instance of the tracking reference class, and we're going to populate the field with a vector of 40 zeros to represent the current count when we start off the game. So I've got space tracking is a new instance of that. Okay, does this make sense to everybody so far? So I've got player reference class. I've got two instances of that, player 1 and player 2, and then I've got a tracking reference class, and I've got one instance of that for space tracking, and they all kind of have been initialized. And then taking a turn is a function, okay? Taking a turn is going to be a function of a player object along with the tracking object, okay? So I'm giving it the tracking reference class and the player reference class, okay? And so what do? We're going to roll the dice, okay? If or you can have if you're not using the manual dice, you can do this, but here we're going to just roll the dice, okay? So that's going to be the roll, and then remember the roll returns a list, and so we're going to take the movement from that number, okay? And then so what we do is we take the player and we call the method move n, So on a regular turn, we just say move n spaces, which is going to be taken from roll movement. And then at the after that's done, remember, keep in mind what move n does is it takes the player and it moves it n spaces and it updates all of those things accordingly, right? And they're reference class objects, so I don't have to say like, you know, update the player, this and that. Okay. Once I have that, then I call the tracking reference class, and we're going to call the method increase count. And where do we increase the count? We increase the count at the player's current position. All right, does that make sense? And so this is a function for taking a turn. Okay, so let's test this out. I'll do set seed 1. And then here we're going to do take turn player 1 space tracking. Okay, it says roll a 6-2, player is at 1, player moves 8, player now at 9. And then we'll do take turn player 2. We roll a 5-4, player's at 1, player moves 9, player is now at 10. Okay, and then we do space tracking tally. Okay, and we can see we have tallied, added 1 to what is this? 9 spaces 9 and 10 here. Okay, I guess I should use you know, and so that's what we have here. My my annotations here are a little bit different because I'm right now using the manual dice. Okay, and then and at player 1 we can see the field for position is that we are at space 9. Okay, and then so here, let me just reset my dice function. Okay, so what I'm going to do is I'm going to simulate a bunch of games here. Okay, so this is how you can run your simulation here. I'm going to just simulate 100 games of 150 turns. All right, so what I'm doing is I'm going to create a new, so when you run the simulation, so right now what you're going to have to do is you're going to have to build a bunch of functions that go beyond, you know, for taking a turn and whatnot. So to run the simulation, I'm creating a new instance of the tracking reference class. Okay, so right here it's we've got a blank vector of 40 spaces. Okay, this is going to be space tracking, and then I've got a loop within a loop. Okay, for the outer loop, we're going to print out new game I, and then we create new instances of player 1 and player 2. And then within on the inner loop, so this is the outer loop's going to run 100 times, and the inner loop is going to run 150 times, which will simulate 150 turns for each game. And what's happening here is we're going to say take a turn for player 1, and then take a turn for player 2. And then we just do player 1, player 2, player 1, player 2. It's going to go 150 times. Now, in an actual game of Monopoly, the play goes on indefinitely until a player goes bankrupt, or until all but one player goes bankrupt. Funny story is that Monopoly was actually created to kind of show the evils of capitalism by showing that the only way it goes is that, you know, the corporations basically put everyone else bankrupt and whatever. But then it turned out when people played, they had fun making each other go bankrupt, and so anyone knows. Anyway, so I guess when you have money, it's fun. But anyway, okay, so you just take 150 turns going back and forth. At the end of 150 turns, then it starts a new game, and then you create 2 new players, and then run 150 turns for that. Then you go back and you start a new game, and so on and so forth. Okay, so I'll just run this. So it runs and it does it pretty quickly. Okay. All right. So there's after 100 turns. Okay, we can see kind of the results of what we have. We're going to take the tallies from space tracking tally. We can actually kind of just print this out, okay, and this is what we see, and we can kind of bind them with the results, and we can see, you know, this is what we have, okay. So this is just pure kind of randomness. No rules have been implemented. It's just rolling the dice 150 times, going around the board, and so at this point, everything's kind of evenly spaced out. You know, some spaces get landed on more than others, but that's mostly due to just random chance, okay? Everything has been landed on about 2.5% of the time, and that makes sense because there's 40 spaces, right? So 100 divided by 40 is about 2.5%. So, you know, the relative frequency is about 2.5% for all of these things. And we can see this is the total number of rolls that we've done, okay? If I were to set my manual dice here and just do this for one of the players, this is, we can kind of see what happens. So here it just says for I 1 through 20, take a turn using this, and here we are kind of declaring our dice right here. We can see this indeed takes the movement that should be implemented, okay? So we roll a 6-4, 5-3, 3-5, 6-2, 5-4, so on and so forth. And we move around the board as such, okay? So what you got to do is you've got to take kind of this. So I've gave you some outline code to begin, and you're going to have to implement kind of the rules for Monopoly, which makes certain spaces land more frequently. So I'll just tell you straight up, jail is going to be the #1 most landed on space, okay, just because there's lots of ways to end up in jail, and then once you're in jail, you're going to spend probably 3 turns in there, you know, unless you break out early, okay. And then, you know, the other spaces, because jail gets landed on more frequently, things that are near jail will get landed on more frequently also, okay? Things that are like, you know, 7 to 12 spaces after jail get landed on, you know, quite often. Okay, are there any questions? You are not required to use the getting started code that I've provided, but you are required to use the manual dice here to kind of show your 20 set turns, okay? So, you know, if you need to modify the manual dice, that's fine. You just need to have kind of these 20 rolls set so that when it gets output, we can see that that these things happen exactly as they should, okay? So that when you roll a bunch of doubles, you get sent to jail, okay? So in this case, turn 8 is probably kind of the most complicated. So, you know, I purposely stuck this in here to kind of show that on the 3rd rolling of doubles, we get sent to jail. So you roll a 4-4, double count is now 1. We start here, we're at 17, we move to space 25. We put a tally at Illinois Avenue, and then we take another turn. We roll 4-4 again. Our double count is now 2. We move to space 33, and we put a tally at space 33. Then we roll doubles, so we took another turn. Now we roll the 2-2. Our double count is now 3, so we go to jail. Okay, and then we put a tally at space 11 jail. So that's what happens if you roll doubles 3 times in a row. So this all happens under turn 8. Okay, and then this kind of shows you what happens when you're in jail. So here we rolled 4-3, we're staying in jail, so we put another tally at jail. Here we rolled 4-4, we rolled doubles, so we're getting out of jail, and we move 8, and we're now at space 19, Tennessee Avenue, and we put a tally at 19 for Tennessee Avenue. Okay. Are there any questions on this Monopoly simulation? Okay. Oh, I've also extended the deadline for the Monopoly homework, just so, because the test is coming up on Thursday, so if you want rather focus your energies now for studying for the test, that's fine, and then you can work on the Monopoly assignment over the weekend. If you want, of course, if you want to finish early, you can do that. Okay, if there aren't any questions, then I'll talk a little bit about the Bootstrap and randomization. I put a little bit of practice up on CCLE as well, okay? So you can have practice writing your own code, and or you can see some code that has been written, and that way when you're asked to write code on the final exam, you would have seen it, okay? Rather than walking into it unprepared. Okay, again, this is not a homework assignment. I'm not going to collect it. It's just practice with the intention of helping you. Okay. So what you're going to want to do is we're going to load library boot. Okay. Now there's this is slightly confusing, but there's library boot and there's library bootstrap. Okay. Bootstrap has some data that we're going to use, but the actual boot functions that we're going to apparently I don't have. Strange. Okay. Boot has the actual functions that we use for doing Bootstrap, at least you know, when I'm teaching you guys. Okay, so here we're going to look at library Bootstrap, and within library Bootstrap, there is a data set called Law82. Okay, let's and what Law82 is, they looked at 82 law schools within the United States, and this is going to serve as our population. We're going to say this is the universe. There's more than 82 law schools in the U.S., but we're going to, for the purpose of this thing, this serves as the universe of all USA law schools. Okay, and what we're looking at is we're just going to look at the LSAT score and the student's GPA. Okay, now. So the LSAT is the test that people take to get admitted into law school, and then the GPA is how the student is doing once they're in law school. And you know, whether that has anything to do with how good or bad a lawyer actually is, I don't know. But here we want to know, is there a correlation between a student's LSAT score and their GPA? And it turns out, yes, there's quite a strong correlation of about 0.76, okay? And if we were to just plot this very quickly, it looks like this, okay? So it seems like there's a fairly strong correlation between someone's LSAT score and their average GPA, okay? Well, it's a little strange. It's the across the 82 schools. So you know, if we look at head of Law82, you know, this is what we have. Okay, their average LSAT and their average kind of GPA and things like that. Okay, and this is the idea that we're going to do here. Is we're going to say, okay, if this is the population, of which there are 82, what happens if we only have a sample, okay? So let's say we had only a sample of 15 of these 82 schools, okay? So again, so if we look at, there's another data set called law, okay? And law is a random sample of 15 of the schools taken out of the universe of 82, okay? So that is this one. We can also create our own samples of 15 by just taking a random sample of 15 from law 82. Now notice how I'm taking the sample of law 82, okay? So law 82 has, if I ask for dim of law 82, it's got 82 rows and 3 columns. What I'm doing is I'm going to say sample from the numbers 1 through 82, I want a sample of 15 numbers, okay? And so it's going to say, okay, it's going to select these 15 rows. It's going to select row 22, row 31, row 46, okay? And so when I do this, and I say subset law 82 so that we are taking those 15 rows and columns 2 through 3, okay? Here, I'm going to actually just do 1 through 3, and you can see that when I look at law sample 1, you can see that indeed I selected row 22, row 31, row 46, row 72, and so on and so forth for this, okay? Okay, and so for that selection of 15 law schools, I could ask, okay, what's the correlation between the LSAT and the GPA? Okay, here the correlation is like 95%, okay? This is just a coincidence that when I look at those 15 random schools that I've selected, they happen to line up very, very closely, okay? Whereas, you know, in the original, the correlation's not as strong. But anyway, you know, here I'm going to just generate 3 different random samples, okay? And so some of them, you know, we have very high correlation, others we have lower correlation, and something in between here, okay? Whereas for the actual population, we have a correlation of about 0.76, okay? And so the central idea of Bootstrap is that the sample we have, because it was selected randomly, is, or we're assuming was selected randomly, is representative of the population. And so we're going to just resample from our current sample and use that to draw inferences about the population. Okay, and so we can try to get a standard error estimate of this correlation statistic. So we have, you know, 15 law schools, and the correlation of LSAT and GPA here is around 95%. We can get an estimate of the standard error here, okay? And so here I'm going to run, here I'm going to do a manual bootstrap, okay? The manual bootstrap is the idea of resampling using the command sample, okay? The automated bootstrap uses the package boot, but here with manual bootstrap, I'm going to do 500 replications. My n is 15. That's the how many rows I have, okay? And we're going to store our results in this vector called results, okay? And so I'm going to repeat NA 500 times. And then I'm going to do this, run this loop 500 times, and every time I'm going to sample, I'm going to create an index of what I'm going to sample, and that's going to be sample the values 1 through 15 and select 15 of those values with replace equal to true, okay? So in this case, if I do this, the rows I'm going to select will be row 7, 1, 4, 6, 13, 13, 10, 12, so on and so forth, okay? And then we're going to subset our dataset law by selecting the LSAT column and those 15 values. Some of them are duplicates. And then we do the same thing with GPA. Then we calculate the correlation between those two things. So here are, the rows that I've selected. This is from row 7, 1, 4, 6, row 13. Row 13, we can see 545 gets selected multiple times because row 13 was selected multiple times. Okay, same thing with the GPA, and then we ask what is the correlation between LSAT and GPA there. Okay, and so for those things, we got a correlation of 0.5. Now, if I did this another time, I would get a different set of indices, okay? And then when I subset accordingly, I would get a different correlation coefficient. And so here I would get 0.75. Okay, so what happens when I do all of this? I run it 500 times, and I can get the standard deviation of those different correlation values. And I have a standard error estimate of around 0.135. Okay, so what's happening here is I'm just taking my sample of 15 values and I'm resampling those 15 values with replacement. Every time I resample those values with replacement, I'm going to calculate a new correlation coefficient. Okay, and I do this 500 times. I get 500 different correlation coefficients. And from there, I can get an estimate of kind of the standard error of our original correlation coefficient estimate here. Does that make sense? What we're doing when we're doing our Bootstrap? Okay. So that's kind of doing it the manual way. There is a function called boot, okay? And boot is very simple. You just say, you run the function boot, you give it the data that you're dealing with, in our case, the law sample, and then you have to give it a function for calculating whatever statistic it is that you're calculating. In this case, we're calculating the correlation between the LSAT scores and the GPA, okay? Now, the hardest part in using the boot function, the boot function is creating a function to calculate the statistic that you want. So the function that you use to calculate your statistic needs to be a function of two arguments, okay? One is going to be the data that you're looking at, and the other is going to be the index, okay? The index works kind of the way we did, where we sampled from 1 through 15, and we got those kind of the rows that we're going to select, and basically that's all you do. You say, here's my data, here are the indices. We subset our data using those indices. We're going to say select all of these rows that appear in this index. And then so that's going to be, we're going to call it D. We're going to say LSAT is that subset data, the LSAT column, and GPA is going to be from that subset of data, the GPA column. And then the value that we're going to return is the last row here, which is going to be the correlation between LSAT and GPA. Okay, so this is a way our correlation function can do that. We can write that a little bit more concisely with just one line where we say data, that we're going to calculate the correlation where we've subset our data using index in column 1, and we subset our data using the rows of index in column 2. Okay, either of these do the same thing. Whichever one makes sense to you, use that one. Okay. Does this function make sense as far as we're going to use this to calculate the correlation from our resampled data. Okay, so the index, you have to just imagine that boot is going to provide something like this, where we've sampled the values 1 through n, size equals n, and replace equals true. Okay, it's not explicitly written in here, but that's what, when you run this function boot and it calls for this thing, the function boot provides this index. And it feeds it into this function here, and that's how it runs, okay? And then so we have our correlation function programmed in here. We're going to say library, we're going to load up library boot, and we're going to just run boot using our dataset law, the correlation function that we programmed, and we're going to repeat this 500 times, okay? And that's going to show up in results, okay? And we can see kind of the structure of results. It looks rather complex. It's not, okay? All of the results that we are interested in are going to appear here in T. If I do results $T, this is effectively the correlation coefficient that was calculated every single time we ran a resampling, okay? And so here I can get what's the standard deviation of these 500 correlation coefficients, and we get 0.1335, okay? Which is very, very close to the correlation coefficient that we got when we did our manual bootstrap, okay? So when we did our manual bootstrap, our standard error estimate is 0.135, okay? That's the standard deviation of all the different correlation coefficients that we calculated here. Here, when we do it here, this is the standard deviation of all those different correlation coefficients. And again, we're getting a standard error, you know, very, very close to each other. 0.13348, 133.5, okay? Or 1348, 1335, okay? So very close. That's the standard error estimate of our correlation coefficient. Okay, and we can do this, we can try running the same thing. We can just so that was using the dataset law, which is a random sample of 15 out of the 82. And again, we've created other samples of 15 out of the 82. Okay, we got loss samp 1, loss samp 2, loss samp 10, and we can kind of just see what kind of estimates we get here. So here we get a standard error estimate of 0.025. Over here, I get a standard error estimate of 0.152. And over here, I'm getting a standard error estimate of 0.054. Okay, so we can see our bootstrap estimates, the standard error estimates, depend heavily on our random sample itself. So remember, the universe has 82 loss goals. Here we're taking random samples of 15, but we're assuming, when we do bootstrap, we're assuming that this random sample of 15 is representative of the 82. And when we run the bootstrap, we're getting pretty different standard error estimates. So we can kind of see how all of this varies, okay? And so what we can do is we can get, we can do a meta study, okay? And a meta study would then be to say, all right, let's just see how much our bootstrap estimates can vary depending on the different samples that we have. Okay, this is only possible because we actually have the universe of 82 Okay, we actually have the population, so we can say, because I have the population, what would happen if I take a random sample of 15, did some bootstrap, take another random sample of 15, did bootstrap, take another random sample of 15, and did bootstrap. Okay, and we can see how all of these different random samples would produce different bootstrap estimates, and then get an idea of kind of the sampling distribution of bootstrap standard errors. if that makes sense. Okay, it's kind of like this. We're further abstracting the hierarchy here, but it gives us an idea of, why are my standard error estimates varying so much? Well, the answer is they vary a lot because the random samples themselves are different. And with Bootstrap, we're making the very strong assumption that our random sample is representative of the population, okay? Which, in the long run, they should be, right? Whenever you do random sampling, they should be representative of the population, but because it's random, with respect to one aspect, maybe the correlation coefficient, maybe it's not, okay? So here, I'm going to create a vector of standard error estimates. We're going to do this 1,000 times, okay? And for each of these 1,000 times, I'm going to, do a set seed. Then we're going to take a random sample of 15 rows out of law 82. After I take a random sample of 15 rows out of law 82, I'm going to run Bootstrap using that sample that I just generated, using the correlation function that I have, and we're going to do 500 Bootstrap replications. And after we do that, we will calculate the standard error of our correlation there. We're going to get the standard error there, and we're going to keep track of that in here. So I'm doing 500 Bootstrap replications for each random sample of 15 rows, and we're going to repeat this 1,000 times, so we have 1,000 different samples of 15 rows. Each of them is going to produce its own Bootstrap standard error estimate, and we're going to see how all of this works out here. Okay, you guys ready? So we'll do this. So it's going to take a little while to run because Bootstrap is doing 500 replications itself, and then we're going to do this 1,000 times. So we'll just let it do its thing. And we'll wait. Okay. But this is kind of the Bootstrap. The idea here is the meta study, and we will. Okay. Well, it's taking its time. Maybe I shouldn't have been so ambitious and asked for it to do 1,000 of these. Okay, there we go. It's done now. It wasn't too terrible. So it took a little while, but not too bad. We're lucky we live in 2017, right? This happening. I mean, in the future we'll say we're lucky we live in 2045, and but whatever. But okay. So what we see here is we're getting Bootstrap standard error estimates anywhere from 0.029 to 0.4, the standard error, and we're getting in the median around 0.12 and something like that. Okay, and we can plot kind of the density of this, and this is most of the time our standard error estimate is kind of in this vicinity. Okay, and so I said, what we see is that the Bootstrap should, quote, get it right most of the time in the long run. Random sampling produces samples that should be representative of the population, and that's the central premise behind Bootstrap. And the idea here is that Bootstrap usually works because random sampling usually works. But again, because it's random sampling, sometimes you get weird samples when you do random sampling. And if you get a weird sample, then your Bootstrap estimates will be weird. All right, that's just how it goes. If you take a random sample and you get a bunch of strange observations in there, but you don't know that they're strange, you're going to think the world looks strange. Okay, that's just how it goes, right? That's all of life. If your experience of life is very weird, you don't know that it's weird. That's your normal, that's what you expect to be normal, right? And then you go out into the rest of the world and you're like, oh, maybe what I grew up with wasn't quite representative. Okay, so anyway, that's what we have here. Okay, I recommend playing around with Bootstrap a little bit. You know, read the textbook, but you know, study the code examples I have here for this, because you're probably gonna have to write some. Well, you will have to write some code on the final. Okay. Here I've got randomization test practice. Okay, in class we did the Mythbusters yawning example, and here we're revisiting that. This time I formatted the data just slightly differently. This time I put the data in a data frame. Okay, and I've done so by taking the factor yawned and taking the factor, creating a factor called group. Okay, and then putting them together in a data frame, so that if we look at data frame itself, you can see there's yawn, yes and no, and then the group is either the seeded or the control group. Okay, and we can see the amount of yeses and nos. And then we can do this by, you know, when you have categorical variables, you can do table df, and you get this, right? And then you can also do add margins to table df, and then it will add the margins for the sum. Okay, so this is what we have, and so we can do we can say the results are this. So this is the results that we have. We have in the control group we have 12 no's and 4 yeses. In the seeded groups we have 24 no's and 10 yeses. And then what we have when we well, what Mythbusters saw was that they said 24 divided by 34, oops, not 24, 10 divided by 34 is 29%, and 4 divided by 16 is 25%. So if we subtract those differences, we get a difference of 4%, and they said that difference is significant. Okay, that's what Mythbusters said. So here I'm saying the observed difference is from the results box 2, 2, which is 10, divided by 3, 2, which is over 34. So this is 10 divided by 34 minus results 2, 1 and 3, 1, 4 divided by 16. So if we do this, we get our observed difference of 0.044-11765. Okay, so this is what we have. And then to run the randomization test, I'm going to just take the vector yawned, which is kind of my factor of yeses and nos, and I'm going to just sample this. Okay, and so when I ask for what randomized is, it's this, and it's just mixed up. We're going to bind those together for our randomized data frame. Okay, and so if we look at the randomized data frame, we got yes, no, no, yes, and they're in the seeded groups. Okay, and then so if I do this, my randomized results look like this. Now I have 3 over 16 versus 11 over 34. Okay, rather than 4 over 16 and 10 over 34. So we have slightly different results. Okay, and now my randomized difference is a difference of about 13 percentage points. Okay, not 4 percentage points, but now about 13 percentage points. Okay, and so the randomization test says, okay, do that same thing, but do it many times. So here we'll do 5,000 replications of this. We'll do each time we're going to randomize, we're going to resample that vector yawned, just shuffle it up, create a data frame, look at the results, and then calculate the difference between those two ratios of square 2, 2 over 3, 2 minus square 2, 1 over 3, 1. Basically 11 over 34 minus 3 over 16. Okay, because that's how I got this number over here. 11 over 34 minus 3 over 16 is this value here. Okay, and then so we're going to do that 5,000 times. We'll let it run. Okay, and then we ask for the summary, and then we see the median difference is, 4%. So our p-value here is, we get a p-value of around 50%. Okay. I guess I forgot for the Bootstrap, you can get a p-value just by asking how often results, your randomized results, how often results $t is, greater than what you observed. All right, does that make sense? Any questions on either Bootstrap or randomization tests? We're feeling okay? We're good? I got a thumbs up there. Okay. Well, with the time left over, I just want to kind of talk a little bit about this plot here, okay? So here, I think you guys are familiar with density curves, right? When you look at when you create a normal distribution, we often express drawing the normal distribution by doing something like this, right? Or if you, if we're looking at a Poisson distribution where, depending on the shape parameters that we give it, it might look something like this, or, we might have another distribution, and I don't know, you get something like this. Okay, I think we're familiar with the concept of density curves. When we have random data, okay, a lot of times we want to look at something that looks like a density curve, right? And so we do this, we have a function called density, and then we can plot it, and it produces this nice little thing, okay? So here, let me just do our norm. We'll take, we'll call x is our norm, okay? And if I do a histogram of x looks kind of like this. This is what the histogram looks like. And we can ask, maybe what's the density? Okay, and we plot the density curve, and it looks like this. Okay, but this represents the underlying data. Here I only have 100 values. If I do like 1,000, and we'll call this y. Okay, so now y, I have 1,000 random values, and I ask for the histogram of y. This looks much more normal, I think. Okay, and here is the density curve based on the 1,000 observations that I have. Okay, and obviously the more observations I produce, the more random observations that I do with z our norm, do 10,000 and ask for the histogram here. Okay, this looks very, very normal, and the density of this is going to look, very, very normal as well. Okay, so, but how are we getting this smoothed out shape here? Okay, well, this thing is called a kernel density. Okay, I think we're very familiar. Like if I told you draw a histogram by hand, here's some data, here's 50 data points, now make a histogram, you guys could do this, right? For a histogram, you say like, okay, I'm gonna create some bins, we're gonna count how many values fit in this bin, and then we're gonna create a bar that's of that height. Okay, that's what we do when making a histogram. Okay, how do we make a kind of a smoothed out curve like this? Okay, if I did, here, let me just show one more thing. Here I'm going to concatenate, combine our norm, we'll say 300 values with a mean of 0 and standard deviation of 1, and 200 values where the mean is 4 and the standard deviation is 1.5. Okay, so if I say histogram of z, it looks like this, and I say plot the density of this, okay, we get something like this. Now, how are we getting this nice kind of smoothed out shape that looks like this? Okay, here's our histogram. It looks kind of like this, and then, you know, somehow we get this magic smoothing. Okay, how does that work? Okay, this is kernel density, and that's what I want to explain. Okay, is how the kernelizing of our data works. Okay, and basically what we're doing. Can I add a rug? Yeah, it's too much, but here I added something called the rug, which shows like the actual values that appear in my z vector, but I've got too many values that we lose a little bit of it. Okay. All right, let's talk kernel density, and this is going to just be a very high level kernel density. Well, let's go back to the histogram. And you know, we're used to seeing histograms. They look like this, right? Depending on how many values we have in certain bins, you know, our histogram might. All of these things are supposed to be the same width. So. Okay, anyway, that's what we have for a histogram. What we can imagine, did I break something here? Okay, all right, I guess we're okay. You know, let's say we had, let's say I had just a few data points here. Okay, let's say I had the data points 8, 8, 10, and 12. Then a histogram might look something like this. Okay, I would get something that looks like this. All right, this is like that. Okay, and we can imagine instead having breaking this down into dropping little boxes. Okay, I'm going to drop a box here to represent this 8. I'm going to drop a box there to represent that 8. A box here to represent the 10, and a box here to represent the 12. Okay, so the histogram can be made by, quote, you know, dropping, you know, we'll say boxes. Okay, so we could just imagine taking a box and then dropping them on their proper location on the number line, and we get something that looks like a histogram. Okay. Kernel density estimation does something very similar. Okay, we're pretty much dropping little boxes, except we're not dropping boxes, we're dropping kind of like blobs, okay? Little kind of flexible blobs or curves, okay? So with a kernel density, we drop little, I don't know, blobs, okay? And so we could let's say I just have an even simpler data set. I've got the data points at 0 and 2. Okay. If I have what we call a rectangular kernel, would look something like this, okay? This is what it would look like with a rectangular kernel. A kernel is basically just a shape, and what makes the kernel different from a block is that the shapes can stack on top of each other, okay? So if I, instead of kernels at 0 and 2, if I had data points at 0 and 0.5, what would happen here is that I would have a block here and a block here, but this block, where this block and this block overlap, they actually would stack on top of each other, and we would get this shape with a rectangular kernel. Okay, so what happens is, you just imagine taking these two blocks, moving them closer together, and where they overlap, they stack on top of each other. Does that kind of make sense? What's happening there? Okay, that's with a rectangular kernel. There's another aspect to the kernel called the bandwidth. Okay, the bandwidth is basically how wide your blocks should be, or how wide your blobs should be. And so in this case, you know, our blob is about this wide. You could have a very wide, if we have a very wide bandwidth, you could end up having, so here's 0, 1, and 2. You could have very wide bandwidths like this and something like this, ending up stacking on top of each other, and then you would have kind of the overlap right here. Because they stack on top of each other, you'd get something that looks like this. If you have with a very wide bandwidth. We probably don't use rectangular kernels all that much, but they're easy for illustrating this, okay? We have, there's also triangular kernels. And basically, if you have a data point right here and right here, your triangular kernel would look, if you just have two data points, your plot would look something like this, okay? And if the bandwidth was increased so that they're even wide, that your triangles were wider, what would happen? Okay, with a wider bandwidth, you'd get something that looks like this. Okay, because basically you have this thing and this thing. Well, maybe if they overlap like that, you might even get something that looks like this. Okay, depending on how the you can imagine these kind of two blobs overlapping each other and forming something like this. Okay, so let me just kind of illustrate what this looks like for you. Okay, so we'll okay, we're going to create a very basic data set, 0 and 1, and then we will do I forget density. How do I triangular? Okay, so we'll start off with we'll do plot density of z, and my kernel I want to be triangular. Okay, so here I have a triangular kernel. Let me see if I can increase the bandwidth so I'll say width equals 0.4. Oh. Width equals 1, width equals, oh, maybe it, okay, well, I guess, oh, maybe it does not fill in each other, I don't know, okay, but this is kind of what we have. So you have, you know, these triangles, as they get wider and wider, they start to, you know, overlap and so on and so forth. Okay, so that's what we have. That's a triangular kernel. Let's do a rectangular. Okay, with a rectangular 1, this is what we have. Rectangular 0.5. We got two rectangles, and they get wider and wider. Okay, so does that kind of make sense what's happening with the kernel? Now the default kernel is not, is probably not triangular or rectangular, okay? Your general default kernel is a lot of times Gaussian curves, okay? So you put a Gaussian curve here, you put a Gaussian curve here, and then with this overlap, you're going to end up getting a shape that looks like something like this, okay? So we have, you know, Gaussian kernels, and then you also have, what is it called? Epanechnikov. It's like a Russian thing. Yeah, Epanechnikov. Epanechnikov kernels. And these are basically upside down parabolas. And so I'll just illustrate what this does. If we have Gaussian kernels with 1, with, so at 0.5 you kind of have these two separate, so again, keep in mind my data here is, we've just got a dot at 0 and a dot at 1, and if I add a rug to this, you know, we have a data point at 0 and a data point at 1. This is what's forming our kernel density estimates, okay? And as we increase the density, or the bandwidth, we can see the shape go, okay? Let me do Epanechnikov. Okay, so we have these upside down parabolas, you know, with a smaller bandwidth, the parabolas are separated, and then, you know, as they overlap, you kind of get this little funny little shape in the middle, okay? These are Epanechnikov kernels. Okay, and so, you know, how does this all look? Okay, well, if Z is not just 2 points, but rather let's do R unif 10 times 10. Okay, so Z, I've got kind of these values. We can do plot the density of Z, okay? And this is going to default to using a Gaussian kernel. And this is kind of what it has. If I do add the rug plot of Z, we can see the 10 values that show up here are at these little lines here. So we got 1, 2, 3, 4, 5, 6, 7, and then maybe like 3 values centered right around 8.9. 8.9, or maybe 9.7, 9.7. I don't know. Okay, I got two values right there, very close to each other, and then a value of 8.5 and a value of 8.9. Okay, so we got a few values that are very close when we add the rug plot, and this is just ends up being the shape that we have. If I do rectangular kernels, we kind of see the more blocky nature of this. This is from one of the data points, and you can kind of see them adding up to each other and forming this awkward shape. And okay, with a triangular one, you get something a little bit smoother-ish. Or the Epinechnikov, that one's really going to be jagged. Well, not super jagged, but a little bit. Okay. But the idea behind all of this is that for each of these, we're just dropping kind of these shapes on top of each other. Just kind of, or if I drop this shape right on top, it would kind of form something like, I don't know, something like that. Okay, kind of fill in the shapes. So we're just taking our kernel shape, whether that be a Gaussian curve or a rectangle or a triangle, and we're just kind of dropping them right centered at each data point, and we just allow the shapes to kind of add up on top of each other to give us our shape here. Now, because of the simplicity of the command, where we just say density z kernel is equal to this, and it produces it so quickly, we might not appreciate the tremendous amount of calculations that go into producing this plot here, okay? Because if you had to produce a kernel density plot manually, okay, and let's say I gave you the simplest kernel, which would be a rectangle, you'd have to kind of figure out, well, and I give you the bandwidth, so I give you everything you need, it's still going to be a huge pain in the butt, because if you have a data point centered at 8.7, you have to figure out, okay, how far to the left and how far to the right does this thing extend, and does it overlap with the kernel rectangle centered at 7.3, okay? And at each location on your number line, you got to figure out how many kernels kind of align and stack up on top of each other to kind of get the exact height that that thing is supposed to be, okay? So, this kernel density estimation is really only possible because of the computer, and it has no problem taking these shapes and just adding them on top of each other. But doing this kind of manually by hand would be unimaginable, because it would require for every single point along the number line to figure out how many, the magnitude of the kernel being added at that location, and how many of the kernels from the different data points get added together. But conceptually it's easy. We're just taking these kind of shapes and we're just kind of dropping them, and they kind of stack on top of each other, and they form whatever shape it is that we are looking at. Okay, kernel density estimation will probably appear again in your future, especially if you study statistics. But and a lot of times we just say, okay, let's make a kernel density estimate without really ever thinking of where it's coming from. But now you kind of have an idea of how this graphic is generated and displayed. Okay, I hope that makes sense. All right, we'll end a little bit early today then, and if you have any questions, I've got office hours today. We'll go until from now until 4 o'clock. Give me a little bit of time to just maybe grab a snack, and I'll be happy to try to help you guys out. All right, with that, good luck as you study, and we'll see you guys on Thursday.